And welcome to the New York City F-sharp user group. Today we have Gina Maini going to tell us about the .NET garbage collector. Thanks.
Hi, the title of this talk is Garbage Collection in .NET, Performance, Extensibility, and Good Old-Fashioned Shoot Yourself in the Foot. Cool, so why are you listening to me? My name is Gina. I'm not quite qualified, but I do work at jet.com and use F-sharp. So I came from OCaml, so part of me understanding what was happening in the runtime for .NET was also understanding the garbage collector. So yeah, this was kind of, I put together this presentation to give internally just to sort of like teach myself and feel like I could understand garbage collector. Cool. So why do we care about garbage collectors? I think the main case in point can be summed up with, like, wouldn't it be cool if we could use more memory than was physically available on the machine? Or that idea of like unlimited memory or not thinking about memory. That it's just, you always have this pool of memory and you never have to think about it. That's kind of the abstraction provided to you with a garbage collector. And so why don't we do this manually? Well, you can, but then you have to worry about these things. So those things are like double freeze, which might mean that you free the same piece of memory twice. So the second time you free it, kind of undefined behavior as to what happens there. Is it some other thing that's in that place now? Is it nothing? Is it a null? Who knows what it is? Dangling pointers are like when you have a lot of references pointing to one place in memory. You delete the object, but those references are still there, and when you dereference them, you might get some other undefined behavior, like what's there now. Memory leaks, which you might have encountered before, which is, you just might see in your profiling tool, memory is going up in terms of allocations. You can't quite figure out why. Efficient implementation of persistent data structures. That's particularly important for functional programming because we like immutability, so we're constantly allocating in rapid succession, and we want to do that in a way where we can clean up objects really quickly and not have them linger around or bloat memory. And then lastly, just programmer sanity. You want to think about your application logic. You don't necessarily want to think about the underlying abstraction of like some memory segment. You want to think about your system. So when you remove that from your code, you just think about your system logic, and there's probably less bugs. Also, it is important to note that for security purposes, like all of these previous things that we mentioned could potentially be security vulnerabilities. So using a garbage collector, you can kind of eschew some of those problems. So some of the terms that you have to understand before we define what a garbage collector is the heap. So this is a little confusing. The heap, while is a sorted tree, is not actually what we're talking about. The heap here is basically a data structure which you have access to, which provides you a pool of memory that you can free up or you can allocate to. So yeah, it's like a dynamically allocated bag of objects. The mutator is the thing carving up memory, basically mutating the heap. So it's saying this section of memory is an int32, this section of memory is some other data structure. A collector is the part of the program that specifically does bookkeeping, like what parts of memory belong to which things. And roots are areas of the heap that can be reached without basically asking any other area of the heap how to reach them. So they're like hotkeys into the heap. So this is useful for, like, let's say you were writing, a Ruby interpreter, and maybe in your Ruby runtime you wanted the definition of an object class. Maybe that would be like a hot place in your heap, or the entry point of your program, or those are sort of what roots are. Now, all of that makes sense? You can please interrupt me if you have questions, because if you don't get this, the rest of this is just talking.
Is it true that there's such a thing as programmer sanity?
Let's come back to that at the end. Also, I'm not quite an expert on that at all. So what is garbage collection? Finally, a definition. Garbage collection is a form of automatic memory management. While the mutator runs, it routinely allocates memory from the heap, and if more memory than available is needed, the collector reclaims unused memory and returns it to the heap. Pretty straightforward. So in talking about garbage collection, there were two main algorithms that came out in the same year, basically. And they both, ways of implementing a garbage collector, and they both had completely different characteristics. And we'll talk more about what those characteristics were. But then later, this paper came out called the Unified Theory of Garbage Collection, which basically said, wait, they're completely opposite for a reason because they're actually two halves of the same whole. They're both going about the problem in different ways. We'll talk more about that later, but the two main algorithms are called mark and sweep, or tracing, and reference counting. So reference counting, what's that? Reference counting is a form of garbage collection whereby each object has a count of the number of references to it. Garbage is identified by having a reference count of 0. So what does this look like? Every time you allocate on the heap, you are paying a cost of adding basically an integer, usually int32, to that object that says like how many references are pointing to it. So you can imagine maybe some of the like emergent characteristics and maybe some of the inherent problems that might come with that. So detecting cycles is particularly hard. So if you have like a reference that's pointing to an older reference that's pointing to a newer reference, or cycles in your heap become pretty complicated. Space overhead, so every time you allocate, you're allocating an extra int32 or whatever you're using for reference counting. Speed overhead, you're doing an extra thing every time you allocate. That does actually bloat over time. It can't be real time, and this is kind of like a longer topic, but basically if you ask for more memory than was available in your heap, it couldn't actually do that. So it has to know ahead of time that you're not going to ask for something ridiculous. So it can't actually be real time. And lastly, no one really uses this unless you're taking like a CS class and you want to like implement one on your own in a toy one. But this is a really important, it's important to know what reference counting is because it really influences some of the performance gains that you'll see in mark and sweep. So what's mark and sweep? I also had some cool quotes here. Yeah, I'm going to read some quotes. So this is from the Unified Theory of Garbage Collection paper. So the incremental nature of reference counting is generally considered to be a fundamental advantage. However, the cost of updating reference counts every time a new pointer is loaded into a register is typically much too high for performance applications, which is basically what I just said. But as a result, some form of deferred reference counting. Okay, this is talking about mark and sweep, so we'll wait for that. So mark and sweep, what is that? The overall strategy consists of determining which objects should be garbage collected by tracing which objects are reachable by a chain of references from certain root objects, and considering the rest as garbage and collecting them. So basically, that can be summed up into allocate on the heap until you can't allocate anymore. Then some other part of the program will count up basically what's alive, and then everything else that's not alive is dead, and it gets reclaimed. That's basically it. It's actually pretty straightforward. And the fundamental advantages, this is another quote, its fundamental advantages are the lack of permutation overhead and the natural collection of cyclical garbage. However, a fundamental disadvantage of tracing is that freeing of dead objects is delayed, resulting in longer pause times. So this is a really cool slide. And this is taken from that paper, Unified Theory of Garbage Collection. And basically on the left, you can kind of see the characteristic, and on the right, you see those two different algorithms. So remember when we talked about tracing, right? So you allocate until you can't allocate anymore, and then you do like a mark and sweep process where you go through, check what's alive and dead. So that is fundamentally has to be done in like a batch, right? So you allocate, and then in a batch, you go through and you reclaim dead objects. Yeah?
So the cost per mutation for tracing, is there a sort of a known amortized cost to that?
No, there wouldn't be, unless now in .NET's mark and sweep there is, because it's doing some other stuff per allocation. But in mark and sweep there shouldn't be. You allocate freely until you have the full CPU to allocate, and then you go through and sweep. So it's not you're not paying the price per allocation, you're paying it in a batch, depending on how you do that batching. Versus if you were doing ref counting, every time you allocate, you've got to check how many things are pointing to it and add that counter. That's the difference. Cool. So yeah, collection style, batch versus incremental. Kind of reiterating what I just said. Cost permutation for tracing or mark and sweep, right? There's none. You're just allocate, 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 and then, right, but for ref counting, it's very high. Where, you know, for most real world applications, it's too high. You can't do it. Throughput on tracing is high, like I said, because you can, I guess throughput here is sort of, I guess, amount of allocating you can do, right? So that's high for tracing and low for ref counting. Pause times for tracing is very long because of that batch process. And real time, yeah, tracing can't be, well, actually I think that's backwards. All right, ignore real time. Collect cycles, also ignore that. So is this like a one versus the other? No, not at all. And frankly, like most of like performance gains in one are usually by pulling in tactics from the other. So all production GCs are hybrid approaches. For every operation performed by the tracing collector, there is a precisely corresponding anti-operation performed by the reference counter. So that kind of is starting to bring them together, sort of. And then this next slide is like kind of a whoa, dude. Like tracing operates on live objects or matter, while reference counting operates on dead objects or antimatter. Does everyone kind of get that a little bit? Kind of like, whoa, dude. So now let's talk about generations, because that's what we really care about. We're here for .NET, Gina, not like intro to garbage collection. So in generational GCs, there's this idea of infant mortality, which is like basically, you know, if you're allocating something, it should probably die immediately, or it should stay around forever. And you have to buy into that. And if you're a C# dev or an F# dev, like just swallow this pill. Understand this really well and take this home with you, because this is the most important idea here. Probably. Cool, so how do generations work in .NET? So when you allocate an object, it immediately gets allocated in Gen 0, which is the ephemeral collection. Newly allocated objects will take up free space in Gen 0. Then if they survive a Gen 0 collection, so they'll do a sub collection. Some of this is not making sense, like future slides will hammer this home, but basically when you allocate something, it gets allocated in Gen 0, which is a segment of the minor heap. It gets allocated there, and then if it survives that minor collection, it will get promoted to Gen 1. If it survives Gen 1, it will get promoted to Gen 2. And objects in Gen 2 tend to stay around forever. Let me see if I'm missing anything. Yeah, there's also, cool. So what happens when a full garbage collection runs? So that was kind of I was talked about minor collections, but now let's talk about what happens when the full thing collects. So full collection, which is also the same thing as a Gen 2 collection, meaning that all objects in Gen 2, Gen 1, and Gen 0 are marked and swept. Is all managed suspension is the first part. All managed threads in the application are forced to pause. Mark, which is the next step. Starting from each root, including our hot roots, remember we talked about that idea of roots, the garbage collector follows every object reference and marks those as seen. So it acts upon those live objects. Then it compacts, so it reduces memory fragmentation by relocating objects to be next to each other. Update all references to point to new locations. This happens on the small object heap when needed, and there is no way to control it. So, but there is ways to control compaction on the large object heap. We'll talk about that later. Or like, what even is the large object heap? Because I just said that word and I haven't even talked about it yet, so don't worry. Then resume, and all managed threads are allowed to resume. Cool. So what's the large object heap? So it holds objects that are larger than 85,000 bytes. So if you look in the debugger, you might see objects hanging around that are smaller than 85K in your large object heap, but ignore that. That's actually stuff that the garbage collector will sometimes steal space when it can on the large object heap, but like the large object heap is, for all intents and purposes, data that's bigger than 85,000 bytes. So usually that's arrays or strings, and it's not compacted automatically for performance reasons, but you can compact it. So here's a slide that I think kind of makes this a little bit clearer. So this might be a T1 or something, right? We've got our different, now this is, here would be the small object heap, and this would be the large object heap, right? Small meaning we've got our Gen 0, Gen 1, and Gen 2, and Gen 0 is all like nice putty ready to be allocated on.
So Gen 0 is really not much bigger than Gen 1 and 2?
In the beginning, but then it looks like this.
Okay.
So in the beginning, Gen 1 and Gen 2 might be just like a byte size because there's nothing there, so it won't take up any space because nothing's been allocated. There hasn't been a Gen 0 collection yet. So here might be T4 or something, right? We've got some stuff that's been promoted through a couple of collections. And note that the individual objects do not move, the boundary lines do. So now, like, what if you allocate something that's bigger than the actual segment size that you're allowed? The GC will actually allocate another segment. And how it actually does this, I'm not super sure. I don't know if it's just like witchcraft. Oh, cool. So I should plug in my laptop. Sorry, what was your question?
When it allocates from Gen 0 into 1 and 2, does it allocate equally? Because it looks like Gen 1 and Gen 2 are growing sort of somewhat symmetrically.
No, yeah, that's a good question. So it would only, so after a Gen 0 collection, basically, it would be moved to Gen 1, and then after Gen 1, it would be moved to Gen 2. So this slide might be a little misleading. That's why it's like maybe T4 or 5. Things have been like a few collections, minor collections have happened already. And I can tell that because, well, actually this one is a little confusing. I'm more talking about this. But a few minor collections have happened. Okay, this is exciting. It's live. Okay. Okay. So a few minor collections have happened, but here, this is like your Gen 2 has become bigger than the allotted heap segment has. So it's going to give you a new segment so you can carry over. That wasn't your, does that answer your question? Okay.
So no, I guess is the answer.
Sure.
So do Gen 0, this is one thing that does Gen 0, 1, and 2 always start contiguous in memory? And then the windows?
It likes to give you the abstraction that it's contiguous, but it's not actually ever contiguous. But the abstraction is that it starts next to each other, and it will try to relocate objects to be closer.
But if it's just moving the lines, isn't it contiguous by default?
Yes, but there's also like paging into virtual memory. It's not actually contiguous ever, but yes, it is like close to each other in virtual memory. And it will like move things around boundary lines to make them close.
So it's not
During
absolutely
compaction.
contiguous.
No, it's not.
So on this slide, you are showing the large objects on a different heap.
Yes.
So
There's two separate heaps.
Okay, so how does it get garbage collected? If I'm allocating something more than 85,000 bytes and it goes to large object heap.
So the large object heap never gets collected.
Never gets collected.
No. You can compact it, you can force that, but it's never collected.
Okay, so you were also talking about two types of garbage collection. That is how I understood it. Maybe I'm wrong. One time it does when the garbage collection runs,
Yeah.
it takes Gen 0 to Gen 1 and Gen 2. And the other one you were talking about is the entire garbage collection runs and it sweeps away all of them from Gen 0, 1 and 2, right?
Yes, correct.
So in the second case, when it runs and does the entire sweep, when does it run that?
So you can configure that, and you can configure that also to be, so you can force it. It runs when basically the Gen 0 and Gen 1 boundaries have reached a limit. So, or it'll trigger full sweeps when it's efficient for the GC to do so. If memory constraints are low, if the segment, if you allocate, and your Gen 1 boundary is pushing that segment, it will run a full collection. And you can have that backgrounded by, or you can configure it to never happen. So depending on your application needs, there's like a few options available to you. But it's kind of like, I don't want to tell you, like I have a slide that's like, when does it run? But honestly, like depending on the actual host, like it might run for a lot of different reasons if you don't configure it.
So when would you run that? When would you run the entire garbage collection?
So ideally you would, okay, so are you asking when would you force a full collection to happen?
When would I force it to happen?
You would maybe force it to happen if you wanted to never then collect in Gen 2 ever again. So like, let's say maybe you wanted to force a full collection and then pin some resources and not have them be collected or something like that. It might behoove you to run a full collection. But it's sort of like, you're kind of playing with fire. Like, is that about right, Paul? You're nodding your head, but like there are points. It exists for a reason. Like maybe you force a full collection, then you don't want to touch things in Gen 2. You want them to be promoted and not touched, which might make sense for again a pinned resource, like an unmanaged resource that's like a system resource, like maybe a socket or something like that.
So can I allocate directly on Gen 2?
Can you? Yeah, you can. You can finalize. Yeah, I actually have like a bit of. I'll show you a bit of code later that will force a full collection. But yeah, you can specify which generation to collect with, that GC collect call.
Okay, thanks.
Okay. But yeah, again, like playing with fire, but you can do it. Totally. And there might be, like, if you were in a trader, like a stock trading thing, maybe during like certain hours, you did not want to run full collections. That might be something you want to do, but then you come into then it's like fragmentation of memory might become a problem because you're never running that compaction phase. So maybe like right before market hours, you run a full collection and then you sort of maybe manage it some other way.
Also, if you want to do kind of high throughput and you run two processes in parallel, you switch to another one, you force full collection on one, the other one still picks up, and then you bring it up once it catches up, then you switch back. So it's kind of, for high throughput.
It's great, but also be aware the sizes of your heaps will be much bigger. But maybe that's not an issue. Maybe that's not an issue for your use case, but because you're not running this, your heap size is going to be big.
I understand what you just said. Maybe we'll take it offline. I had another question on it. Like, I don't know, why would you, I know the advantage of it, but again, if you are creating another thread, right, and then you are doing a garbage collection on the other thread, it still does the garbage collection from the memory, right? It's not...
It's two different processes. So basically you pre-allocate, you allocate the entire thing on each process.
Okay.
And then you choose when you want to switch to another one. And then you force garbage collection, so you start fresh for each one, individual process.
Thanks.
I never thought I'd hear the three words behoove garbage collection together. That was fabulous.
At least they're an add-on, or at least it's not
Garbage
collect,
collection.
behoove, garbage.
So, so some characteristics of this type of generational pattern is that, the time that it takes to do a garbage collection depends on the number of live objects. So what I mean by that is, like, you could allocate a tree of 1,000,000 objects within your function, but if you don't have a reference to them, it's totally free because it basically will get immediately collected. And that immediate collection will be a partial collection on Gen 0, so it'll be very cheap. This is really important for things like F#. This is really great. This is super great for F# because we love our little functions with immutable data, copying, transforming that data, returning that data, and that all gets collected really nicely. So this is we just talked about this. When will collections happen in .NET? When memory is low So that's, again, something you can't necessarily control, but I mean, it's something to be aware of. When the memory that is used by allocated objects on the managed heap surpasses an acceptable threshold, this threshold is continually adjusted as the process runs. Adjustment here might be like allocating a new segment of memory from the GC. The GC collect method is called, and yeah, for unique situations in testing, you know, like I wrote some code that calls GC collect, and this here would be a full collection, but you can specify which generation you want, stuff like that. Yeah, so now talking about the two different types of modes, or two different garbage collectors. So there's the workstation GC and the server GC. Excuse me. Workstation GC is the default GC, so when you're hacking on your laptop, that's what you're using. There's some differences here. The thread that triggers the collection, so once it allocates, can't allocate anymore and has to run a collection, that same thread is the same thing that's doing the collection. It can't background that work. Or I think actually you can if you specify it. But basically it's per logical core, I believe. So like with one processor, that's all you get. You can't background that, which kind of makes sense. There's no way you can do that well. So for server GC, creates a thread per logical core. These threads run as thread priority highest, which I actually don't even have any idea what that means, but that's on the slide. After a garbage collection, these threads sleep again, and there's a separate heap for each processor. Collections can run in parallel, and allocations can happen faster. Yep, go ahead.
So I was just saying the thread priority highest is what I know is that when it does the context switching, it kind of runs the one which has the highest priority first, but it's not guaranteed again.
Cool. So yeah, a single thread, trigger collector makes sense on a workstation, but not a server with maybe many managed processes. Other configuration options, you can, background garbage collections are enabled on server by default, but you can turn it off. You might want to turn it off if you start to notice diminishing returns, and that's kind of like a more advanced topic, but some people here, especially at JET, have probably noticed certain diminishing returns on server GC. I'm sure afterwards they'd love to talk to you about it. Low latency mode, which is for workstation GC only, suppresses Gen 2 collections. So that's pretty useful for that, maybe that circumstance I talked about. Maybe you've got a pinned resource that you don't want the garbage collector trying to unpin. I mean, pinned resources aren't a big deal unless it tries to unpin it, right? So just turn off GC2 collections or Gen 2 collections if that's what you want, and maybe that's good for your application purpose. Sustained low latency for workstation and server GC will suppress Gen 2 collections but allow background Gen collections. So that also might be useful if you want to background the collection, but maybe you don't want the thread that triggered it to run the collection. And again, both of these modes really do increase the size of the heap, and depending on your use case, that might not be acceptable. Yeah. Here are some example app.config options, kind of like what we're talking about, but you can also call them from your code. And just as a topic of interest, what is the size of the ephemeral segments, Gen 0 plus Gen 1? So you can kind of see, here's sort of what it looks like on different architectures with workstation GC, server GC, and then changing the number of CPUs. And I'll add these slides on the meetup too, if you guys want to look at this later. So things that you might not expect about the .NET garbage collector is the frequency of collections is determined by how much memory is allocated in a specific gen. So what I mean by that is, depending on how much you allocate within a generational cycle, is how much it'll run. So you allocate a lot, it's going to try to run collections more often. And the thresholds adapt, basically when those boundaries get hit, are based on the processor's behavior. So if there's not a lot of memory on the machine, it'll try to keep the heap smaller and it'll run collections more often. So some optimizations to keep in mind: reduce allocation rate, which sort of makes sense. Like, do I really need this object? Does this have any fields I can get rid of? Can I reduce the size of my arrays? Can I reduce the size of my primitives? You know, maybe I don't need it in 64, maybe I can use it in 32. Init when needed, make things structs, you know, or just like think about your code differently. But I mean, I don't know. Yeah. Reduce depths of trees. Because it's mark and sweep, if you've got really deep trees, then it'll take longer to run a full collection. So that kind of just means is like, if your code is really complex, it's going to take a long time to collect your code and make sure that everything's free. Reduce references between objects. Avoid finalizers, avoid pinning, maybe, but like you need them sometimes, so maybe don't do that. Avoid putting things on the large object heap, except when you need to, right? It's like, I mean, like all of this is with a grain of salt. It really depends on your workflow and your workloads. But you know, the large object heap, unless you're like forcing that compaction, it's not going to be compacted, so you can deal with fragmentation issues pretty quickly. Pool long-lived large objects. Cool. So a note on finalizers. So finalizers are code that's triggered by the garbage collector to clean up managed resources. So you know, you implement a dispose function to get rid of unmanaged resources. But I think like the thing that really I didn't necessarily understand was that the CPU is going to dedicate more resources to cleaning up your object, and this object will live longer than it would have if it had just been, it lives longer than the collection that should have killed it. So keep that in mind, but this pattern exists for a reason. Cool, so this is kind of the end of these slides before we get to code. Is there any questions? Are there any questions? Yeah.
I might have missed this. At what point does something get moved from Gen 1 to Gen 0 to Gen 1?
So after like a partial collection is run through all Gen 0 objects, so after it's allocated, it hits that like internal threshold boundary of Gen 0 and where Gen 1 would begin. It triggers that collection, and then whatever lives from that like minor collection of Gen 0 gets promoted to Gen 1. So it just moves that boundary line, it compacts, moves the boundary line, and now that stuff is in Gen 1. And then same thing, it'll allocate until in Gen 0, do another, fills up, and then Gen 1 will get bigger and bigger. When it reaches that threshold, it'll trigger a full collection. Yeah.
So,
oh, sorry.
So how close to true is the statement? It is free if it gets collected at Gen 0.
Very true.
Okay.
Yes. Unless it doesn't go to Gen 0 and it goes to the large object heap, and then it's a big thing and it's not free.
But that means you have 8,500 or 1,000 bytes.
85,000 bytes in size. Yeah.
So that gives you a lot of room to do stuff. If you're creating things that are that big.
Yeah, I mean that's the idea. Is if they're that big, then they should have their own heap, and we should think about them differently.
Right.
Yeah.
Is it possible to manually trigger compaction of a large object heap?
Mm-hmm.
It doesn't happen on that.
Yeah, there's a good example in this book. I can show you after. I don't have a code sample of that, but I've got right here.
So when you showed us a slide where the line moves between garbage collector 0 and 1 and 2, you said this is pretty important slide for us to understand. Why would I care about the movement of the line? Because for me, it's still generation 0, 1, or 2.
That's correct. Like, why would you care? I mean, maybe you don't. I think it's just like, it was useful for me to understand like when collections would be triggered. So like, let's say you have let's say your use case is you are allocating some object per like a request or something. And every time you make that request, the object is bigger than the boundary line in memory for when Gen 1 begins. So it triggers a partial collection, or maybe it triggers a full collection. I think just like understanding that can happen, or understanding how these boundary lines move through time is useful. But yeah, I mean, think about it in generations or in terms of like boundary lines moving, whatever makes more sense for you.
And what are the best practices we can follow, like, you know, for so that we, you know, if you can talk about some best practices we can follow while coding, so that we don't even get into issues like this if we follow them kind of rigidly?
Yeah, I mean, so this slide kind of has some stuff on it, but if you want to go into like in depth on how to optimize, I can give you some more in-depth answers than this. But basically, yeah, just understanding when things are pinned, either explicitly or implicitly, will affect, like, basically, is this thing unmanaged? Can the garbage collector not try to, like, how, basically, if you're going to pin early and let it get promoted and then leave it. So that might be one strategy if you've got a pinned resource. But, yeah, I guess just knowing how dispose works for your iDisposable thing that you're using. And yeah, I guess allocate within function closures, I think would be another good best practice. Like, make sure that it can be cleaned up quickly. If it's within that function closure, it'll get cleaned up in a Gen 0 collection, which is very cheap. Versus if you kind of have something that's hanging around in some other scope for most of your program, it'll probably get to Gen 2. Unless it's a full collection, it won't ever get cleaned. So yeah, and then, you know, in terms of like real world diagnosing that's when profiling tools come into play. But usually, I mean, I would say most people probably never reach for these, but some people really need them. Like, it just depends on your workload.
What is the book you're talking about?
This one is Writing High-Performance.NET Code by Ben Watson. Very good.
Can you talk about some use cases at Jet where you needed to do optimizations? And
I've been there for like 6 weeks, so like, no. I'm so sorry, but I have nothing for you. This is also like 6 weeks of F#, so like, bear with me, guys. Okay.
So kind of very generally speaking, the longer things are referenced, the more likely it is they'll end up in Gen 1 and Gen 2.
Totally.
And not be
And the more complex those references become, and that reference tree is, the more likely it'll be harder to collect, and those collection times will be longer.
So when I first started, I started like I wasn't properly trained at all. So I had this idea in my head that was like, avoid creating new objects. Just like stash, you know, like put it in a private field and reference it. And is that basically why that's a kind of a bad idea? Is because does that make it more likely that it's going to
avoid using objects?
No, I mean, I had this idea where I would avoid creating like a new instance of a type or an object.
I think anytime you can avoid creating a new, like when you create a new object, it's got references to whatever parent class or whatever. I mean, if you can avoid creating a new object, avoid creating a new object. I don't know if I can say that. Or if you can use a struct, like great, use a struct. Or like if you can encapsulate this in some other way that can be cleaned easily, do that. But also if you're like creating this object and then the lifetime of that object is quite short, then it's also not a big deal. But I think it just depends on like how big your object chains are.
Okay.
Does that kind of make sense?
Yeah.
Maybe not. Yeah.
So does this mean like F# linked lists are extra terrible because it has to fuck the whole thing to each reference cell to figure out the garbage collector?
No, but I can't exactly tell you why it's not awful. But it's not awful. I think you should talk to Paul.
Maybe later.
Maybe later. Okay, cool. So also, this is my works cited. This YouTube video is a really great Papers We Love talk on the unified theory of garbage collection. I really recommend it. It's really fun. Also, the paper itself and the interwebs. So now let's see if I can run some cool examples. Maybe not so like it's not super cool, but it'll show you some stuff. All right. Okay, you guys can kind of see, but not really. So, let's see how we do this. Yeah. Nope, that's not what I want at all.
There's a little like percent, 100% in the bottom left there.
Yep, that sounds good. This
Yep.
isn't even out.
Control scroll wheel.
Control scroll.
This is exciting, but it doesn't get away this magnifying glass. This is like an acid trip. My God. Okay, I will give pizza to anyone who can tell me how to get rid of this thing.
I don't even know what that is.
Windows.
At the bottom.
Minus.
Windows and minus. No, it just zooms out.
Okay,
Cool, so
there's
this
a
is
little
awful.
transparent
Control
thing at the
Alt
upper left. There's
Have you tried restarting your machine?
There's a
Oh,
little
man.
widget on the upper
Wait
left.
15 seconds, turn it back on.
This is
See the
so
transparent
bad.
magnifying
Okay,
glass
I'm just
over
gonna
there?
click something.
There's a
No.
transparent magnifying glass on the upper left.
Oh, really?
Yeah,
That sounds
yeah.
like what I want. Upper left. Yeah, this thing.
Yeah, click that.
That's it.
Okay, cool. So
Take it to
now
minus.
get out of my way.
Minus.
Whoa, yay!
Yeah.
That was
Who says
exciting.
parent doesn't work?
Yeah, I'm very okay. Cool, that's bad. Awesome. And now we know how to get rid of it. Okay, cool. So let's just make this a little bigger. All right. Okay, so this was a really great example that Leo sent me, where some gentleman was like, "Well, what if I implemented tuples with a struct? Like, how much bigger?" How much harder or faster would it be to spend time collecting it? So pretty simple here. All of this code should pretty much look familiar, but basically creating a type of alpha beta, which returns basically a new tuple record type versus the default tuple type here. So in this tuple code difference, I create like a size of an array. Then, for the init, it's got 2 ints here. Then I mutate it. I call gc-collect. I start a stopwatch. I add something. I mutate on it. I call another collection, and then I stop. So I want to see how long it took to do all of this, basically. And then it's going to print how much time it spent in garbage collection. And then here, I restart my watch, and I use my handy-dandy pair type, which I made. And I do the same thing over again. And then we run it with time. So now let's see.
Why are you doing the mutation of the first element?
I think to create a reference to reference it.
Okay.
But we can also take it out and see what changes. Cool. Yay. All right, so what happened? Something happened. So in this gentleman's case, he wanted to see what the difference in time would be between this. So his struct tuples took about 300 milliseconds in garbage collection, while this one took a little over 1,000. So that's a pretty big difference. So imagine if you had to iterate through something and allocate tuples. Maybe it would be more performant to use structs, and you wanted to see what the actual difference would be in the collection time.
So those were tuples of int star int, right?
Int star int? Yes. Yeah, you mean yes. So just a basic default tuple versus his pair type, which was just a struct.
So what is the difference between the two for non-F# developers?
Just how much size it takes on the heap to allocate it, and how easy it is to clean it up.
So why is struct taking heap allocation?
Why is struct taking heap allocation?
It
To
should be-
allocate a struct on the heap takes less space than to allocate a tuple. And I don't know why, but it does. And he wanted to see what the difference would be if he created his own data type that was just a tuple, but it was a struct under the hood, versus using the default tuple.
I call those stuples.
See, I would expect this struct array essentially to be on the large object heap because you're allocating a lot of them, right?
Well, we can change the size of the array. Let's make it size 5, and let's see if there's a difference. Start with that. Did it really run that fast?
But shouldn't struct be
Yeah,
going
so
to
there's
this-
still, there even still is a difference, but it's actually a lot smaller. I don't know why.
Well, because I guess when arrays are small, .NET might be able to do some optimizations around that.
Yeah, potentially.
This is the wizardry we deal with every day.
Yeah, I don't know. Default is still spending less time in GC. Okay, I don't know.
Does this mean my package gets here next week instead of this week?
Oh, God. Okay, my next example is leaky memory. So after that example was a disaster, let's try this one. All right, so in this, I basically just create a loop which like does this async expression and allocates like a big array. And I keep doing this every 500 milliseconds. So I just wanted to see what would happen if I looped infinitely and kept allocating a big array. I just wanted to see what it would look like in memory, because I didn't really know what it would look like. So let's see. So the way that so first let's just see it loop. Cool. So here it's looping. Every 5 seconds, it's going to print loop. And every 5 seconds, it's allocating this like async array thing. So now I wanted to see, okay, well, what does this look like over time? Like, let's say I had an application where it was leaking memory. What would it kind of look like? So here, because I did a couple examples with VMMap, and honestly, like, there's a lot of bells and whistles, and that's like a whole other class. So I just went to Visual Studio and did like start diagnostic tools, did performance wizard. Cool. Okay, .NET memory allocation. That sounds like what I want. Stress testing. This sounds good. Cool. Finish. Yep. Let's do that. Sounds good. Cool. So now it's running it. And after a certain period of time, we'll kill it, and then we'll kind of see what it looks like when you write troll code. Cool, so now it's creating this profiling report, which all of this stuff shipped with like .NET 4.5, I think. Like all of these like really, like they put a lot of work into profiling with garbage collection, like a ton of work. So now it's analyzing this report, and you can see this little progress bar. So this will take some time. Talk amongst yourselves, eat some pizza. It's Visual Studio. You can hear my computer sounds like it's taking off. Let's see, I can probably show you some previous reports, but I don't know. Maybe they've been deleted. I
feel the heat coming off it over here.
Yeah, it's quite loud. I mean, I don't know if you can hear it, but it's really taking a long time.
I need a beer.
It's getting too hot in here from all the CPU usage.
The real cause of global warming, Visual Studio.
So regarding the structs,
Yep.
Is that a special example, or is it the same like I've been taught like structs live on the stack, right? And when you pass them between methods, it has to actually copy that memory around. Is that true?
I don't actually know. I don't know the
Okay.
answer.
If you've got structs in an array, then the array is on the heap, and it's full of structs, and they're contiguous. with this
Okay.
heap.
Yay! Cool. So now we can go in here, and this is kind of a summary of what you might expect from this program. So you can kind of see like T0, we allocate a bunch of stuff, then slowly over time, the heap starts to like blow up a little bit. And this is through CPU usage on the right. And here's the call tree. Let's see. There's a ton of really cool tooling in here, actually, that I really want to spend a lot of time playing with. But yeah, you can see a call tree of everything. Let's see if we can find allocation. So here, you can see my tuple array here. Inclusive bytes. That's a big number. Big numbers. And here's some of the mark and sweep process. So each of these are ID'd. And this is really useful if you want to see why a resource never got cleaned up and it was pinned. And actually, a lot of other profilers will do this a little better, but this kind of is like an all-encompassing profiler, and it's just easy, so I picked it. And yeah, the rest of this stuff is process level information, so if you had like background stuff doing work, you could see that under processes.
Gina?
Yeah.
Do you know, is there a particular minimum SKU that this tooling comes with for Visual Studio, or is it in the box in all the editions, or?
I think this ships with diagnostics, right? Like, so if you have system diagnostics, this should all work.
Is it really?
Yep.
Wow.
Yeah.
That is impressive.
Mm-hmm.
Maybe only as
Yeah, and you can export this report in like all types of formats. It's kind of neat,
That's
actually.
very cool.
Yeah, and then so you can walk through the called functions.
Nice.
Yeah, you can walk through the stack, which is neat. Now my stack is pretty simple, it's just a recursive loop, but yeah, you could understand like maybe why this would be super useful. This is inclusive allocations, inclusive bytes, so it'll tell you how much the byte size is for allocation.
On the performance version, it'll show you hot paths with the code and all that too.
Mm. So they're trying to put red cat in business.
Cool. Yeah, so I'll just like, I'll throw up the slides and make sure the code samples are there, but they're pretty simple. So thank you for listening, and garbage collect all the things.